Welcome to the WOSP-C 2020 Invited Talk on Automated Scalability Assessment in DevOps Environments. Our team works in an open collaboration model for technology development with presence in several continents. Here are a few highlights of my career. I am the founder of eSulabs Solutions, which is focused on the research and development of automated scalability assessment tools for DevOps and microservice architectures. Site crashes due to scalability issues can have significant impact on business success. Some examples of software scalability site crashes due to overload conditions are the Canadian immigration site that crashed after the results of the last American presidential election was known. Recently, New York State Labor website crashed to the surge of coronavirus-related unemployment applications. These are rare but painful events that need to be planned for in business continuity analysis efforts. A more common cause of poor performance and scalability is the lack of proper software engineering, including performance and scalability engineering. Application performance has a direct impact on business success, as it impacts perception, trust, and sales. 50% of online customers leave the website if the site response is larger than 2 seconds. Only 40% of the customer will return after having experienced a performance problem. The chart shown in the slide illustrates the user perception of performance. Immediate response is perceived if the response time is less than 0.1 seconds. User notice delay, a sense of flow is lost when response time approaches 1 second. User loses focus when response time increases to close to 10 seconds. If response time is larger than 10 seconds, users initiate different activities and need to do a context switch for each interaction with the site. The operational profile is a quantitative characterization of how a system will be used. It supports increased productivity, performance, and scalability if testing is prioritized, taking into account operational usage. The slide illustrates some of the several ways the operational profile can be represented as a load versus observed load situation, as an histogram, using behavioral models, and mix, or as a table. DevOps is a set of practices intended to reduce the time between committing a change to a system and the change being placed into normal production, while ensuring high quality. Some of the practices used in DevOps are automation of development and testing, continuous integration, continuous development pipelines, microservice, production monitoring, fast feedback to developers, use of heterogeneous technologies, agile methods, and many other technologies. In this talk, we address some of the challenges and opportunities to implement performance and scalability testing in DevOps environments. Specifically, we propose a methodology called Production and Performance Testing Application Monitoring to integrate established quality assurance methodologies while supporting DevOps practices. The PPTAM approach creates a tool ecosystem that integrates operational data collected from production that is used to weigh load tests through application performance monitoring integration. We introduce a new approach to measure baseline scalability requirements using bench flow integration. We define a scalability metric that allows for quantitative comparison of deployment alternatives, and we provide integration to mobile device dashboards. In addition, as future research, we propose to integrate the proposed approach with performance anti-pattern detection and refactoring models. Load testing is the process of assessing the system under load in order to uncover load-related performance problems and certify the system ability to meet performance and scalability requirements. One of the key roadblocks in integrating load testing and DevOps is the lack of performance requirements that can support the definition of load testing pass-fail criteria. In this slide, we illustrate how the PPTAM approach automates the definition of pass-fail criteria. The operating point scalability test is depicted in the slide by the solid black vertical line. A low load test measures the average and standard deviations of the response time. Scalability requirements are defined as the tolerated response times for System 1 and System 2 by computing average plus 3 standard deviations of the no-load measurement. As can be seen from the plot, by following the bold black line at the operating point scalability test, System 2 passes the scalability test, while a non-scalable system, System 1, fails the scalability test. The main assumption behind the approach is that the response time curve increases as a function of system arrival rate, proportionally to the inverse of 1 minus utilization of the bottleneck resource, as illustrated in the slide. The classic load testing approach is prone to many problems, such as high manual required effort for maintaining load tests, the lack of suitable load tests, the need to lengthen execution times, and the requirement for complex analysis of test results to detect performance problems. In modern continuous engineering scenarios, there are multiple individual pipelines that aggravate the classic load testing problems. First, releases are very frequent, and the agile process does not provide sufficient time for test execution. Pipelines are automated, so there is no room for manual intervention. Pipelines usually focus on single service among several possible ones, and there are no suitable load tests for each of them. It's very hard to execute complex load tests every time due to frequent releases and parallel test execution, and the analysis of performance problems in these environments is even more complex. To address the integration of performance testing to DevOps continuous integration, continuous development pipelines, we have developed a ecosystem for production and performance test application monitors that employs relatively short 30-minute tests that can be continuously integrated into the agile process and are used to assess architecture deployment alternatives and to create a domain metric dashboard that includes automated pass-fail criteria measured at low-level loads. In the following, we present empirical results derived from the application of the PPTAM approach. The challenge we address is to assess performance of architecture deployment alternatives as defined, for example, by number of replicas, CPU memory allocation, or technology stack, under fuzzy requirements. Our approach uses operational data to generate and weigh load tests. It automates the measurements of baseline requirements and generates a metric that allows for quantitative comparison of deployment alternatives. It's built on previous work from telecommunication systems. The work we present in this talk was initially published at the European Conference of Software Architecture in 2018, and the extensions to the approach using the domain metric to detect security attacks was accepted to publication at the Journal of Software and Systems 2020. Our approach starts from production data that are collected and analyzed to identify the different load situations the system is subjected to in production. From the production data, we determine the empirical distribution for different load levels, computing their relative frequency of occurrence. Then, to reduce the expected number of executed tests, we aggregate the relative frequency on given load levels, and we derive the sampled load tests. Once we have sample load tests available, we are able to issue the test against a given deployment configuration of the system. Along with the test, we also execute a baseline test to measure the system performance with low load. Then, by using the scalability criteria, we can determine the pass-fail criteria for each configuration for different loads. An example of a scalability criteria is defining the accepted deviation from the response time measured in the baseline test. In this application used average plus 3 sigma of the low load measurement. The assessment is made by analyzing the response time for each single call to the API of the system that are part of the defined workload, and then the data is aggregated. On the next few slides, we are going to go through a detailed example of the operation of the approach. After executing all the tests, we can compute the KPI we call the domain metric. The maximum value of the metric is 1 and would be achieved if all tests pass. We have applied our approach to the Sock Shop microservice application, which is composed of 12 microservices and was released by Waveworks. We extracted 6 load levels from production data and sampled 6 load tests, issuing a custom defined operating mix. We issued the sample load test against 10 different architecture deployment configurations with a scalability criteria on response time, defining as acceptable performance a response time of at most 3 standard deviations from the average response time obtained in the scalability test. Here we see an example of a deployment configuration with 1 GB RAM, 0.25 CPUs, and 1 replica. We consider the custom operating mix on this slide, where we have 3 calls to APIs: get cart, and post item, where post item failed the scalability criteria. By relying on the analyzed production data, we have obtained the aggregate relative frequency for each load situation when the number of users range from 50 to 300, as shown. Let us consider, for example, the load test for 250 users. Then, the maximum contribution to domain metric for this load is 0.20370, which is the aggregated relative frequency of occurrence of that number of users. But since one of the APIs fails the scalability criteria, the actual contribution for this load test is 0.13580, which is obtained by removing from the 0.2037 the contribution of the failed test. Similarly, when we execute all the load tests for all the defined load configurations as shown in the slide, we can compute the domain metric for all of them. Finally, we can compute the domain metric based on defined pass-failure criteria. In the case of this example configuration, the actual computed domain metric result is 0.77631. By repeating the experiments on all the access architecture deployment configurations, we obtain the results shown in the table. The example we described before, marked in blue, is the best performing configuration for the sample production load. But as we can see from some other configurations, that configuration we have expected to perform better because of higher number of replicas for one service, marked in red, in fact performed worse. This result demonstrates what can happen when adding additional results without the proper engineering analysis. We then compare the single contributions of the sampled load tests, where the blue line represents the maximum possible contribution for the given load test, and the single lines represent the contribution to the domain metric for different deployment configurations. We see how the violet configuration has the best results for up to 150 users, but the green configuration is the overall best performing configuration. In summary, PPTAM collects the operational profile of a microservice system, automatically runs a series of experiments with given usage profiles and probability of use. It runs experiments according to templates that control time, number of agents, and single operation max response using Faban. It set the goals of testing, for example, resource configurations, and collects data for each experiment or multi-experiments using BenchFlow. It identifies failing services using baseline thresholds according to R scripts in Jupyter, and computes the performance metrics of non-failing service for each service configuration, CPU, memory, and replicas over workloads using R scripts. We now move to the second part of this presentation, which is how to identify scalability impacting architecture components. So we apply the approach to a large telecom, and here you see the PPTAM with the different factors that we have added. One is Mirai attacks that can reveal the impact of security attacks on the domain metric, and it's the topic that was presented at the JSS journal. I recommend you review if you want more details about that. We see the integration with the application performance monitoring, influx data to collect the production usage. And as future research, we are going to present an architecture cockpit with the idea of identifying which of the components are bottlenecks into the scalability of the system. So after scalability problems are detected in load testing, it is important to apply performance engineering techniques to identify the architectural components that need to be refactored to enable greater scalability. We have applied the PPTime approach to a large telecom system, and we present in the next slides the analysis of the scalability test results. Classic scalability test logs usually use the format of response time measure, load, and service. These logs lack support for path failure criteria definition, failure identification, and prioritization for component refactory. So what's the problem with the log that you see in the figure here? It's that lots of script developing and manual analysis needs to be performed to identify what's really going on. Once the PPTime approach for baseline scalability requirements is used, we can plot each scalability test into one of 4 quadrants as shown in the figure. So we are dividing the state space of components according to normalized distance being less than 1 or greater than 1, and the slope of the scalability regression line being less than 0,1 or greater than 0,1. So we see that we can identify components that need to be analyzed for possible refactoring and for anti-pattern matching by looking at the upper right quadrant, where we are violating both the response time requirement and the scalability slope. As you can see from this figure, it's very hard to sort and identify which are the components that are critical to the scalability, specifically the ones that are very close to the 0,1 slope. Our objective is to support component prioritization. The next slide shows a data sample of the plot for loads that were measured at 90% utilization of the transaction rate. So the actual data provides insight of which component should be analyzed for refactoring. However, it's hard to sort on 2 variables and to understand a detailed hierarchy of the paths. So a partial order of the data is shown in the next slide in the format of a Haas diagram. In a Haas diagram, we look at the paths from high to low in the diagram, where in each layer there is a weight computed for that is similar for all the components the same layer. So in this figure, components at layers 1, top layer 1, 2, and 3 would be most likely to be candidates, and it's easier to visualize using a Haas diagram. So in summary, DevOps provides access to real-time data and therefore enables production data and scalability testing integration. The considered use case presented in this talk were performance and scalability. However, other utilities like survivability, resilience, security can also be supported by PPTime approach, as the extension shown in the JSS paper. The approach presented in this talk can be used to provide detailed guidance to architects and developers in real time by using domain metric-based scalability assessment dashboard and by doing detailed analysis of the components. We can support prioritizations and components and also look into refactoring of component based on load testing results, as future researchers are looking to connect the multivariate analysis with performance anti-patterns. For further reading, please refer to the following publications. PPTAM 2 ecosystem is presented on the PPTAM production and performance testing based application monitoring that appeared at the ICPE companion proceedings in 2019. The technical description of the approach is presented in detail at a quantitative approach for the assessment of microservice architecture deployment alternatives by automated performance testing, published at the European Conference on Software Architecture in 2018. Extension to detect security attacks were presented in Scalability Assessment of Microservice Architectural Configurations, a domain-based approach leveraging operational profiles and load tests. Journal of System and Software, appeared in early 2020. For further information about the topics presented in this talk, please feel free to contact me at beto@esulabsolutions.com. Thank you very much for your attention, and again, feel free to contact me.